Welcome to the Kirk Lecture, part of the program we're having on connections between number theory and physics. And we're very happy to have Taormina today giving a talk about counting states in string theory. Thank you.
Well, thank you. I mean, I'm very humbled to be giving this Kirk Lecture today. And I would like to thank everybody here who made it possible for this to happen, and in particular the organizers of the program that Michael just talked about, because they're doing a magnificent job. The second thing is that this lecture is really aimed at people who are not directly involved in string theory or haven't been. So I can see a few in the room, but I also see a lot of people who are real world experts in string theory. So hopefully they will enjoy whatever I say, knowing that they know it already, and maybe with many more details than I will be able to present today. So what's the plan? Well, the plan is easy. I want to give some life to that function there, which is a function of two complex variables, because when you shake this function in the right amount of energy, you will see a beautiful phenomenon appear, which is actually a puzzle to this day. Now, this shaking happened in 2010, but of course, it was very much prepared by work that was done since the mid-80s. And I would like to take this opportunity to thank my collaborators who are more directly connected with this story, past and present. So I would like to thank Toru Eguchi, which I met for the first time in '86 and knew until his untimely death, unfortunately. Then Catherine, who is my other long-standing collaborator since the shaking of this formula. And then more punctually, I had collaboration with Hiroshi Oguri and Sung-Kil Yang back in the days, and more recently with Matthias Gabadil and Roberto Volpato, who is in the room today. So let us start by counting states in a theory which is in principle as simple as possible when it comes to string theory. Because that function I showed you before is actually a function that counts states, but it counts states in a very specific way that I hope I will be able to convey towards the end of the talk. So the bosonic string, and I'm going to talk today about closed bosonic strings. A little picture there that I'm sure everybody is familiar with. You have a string loop here, which evolves in space-time. The embedding space I call E here, which has a certain metric capital G mu nu. And as it evolves, it describes a two-dimensional surface, which is called the worldsheet sigma. The parameters of this worksheet I call x0 and x1, and I've chosen the length of the string to be 2 pi, but obviously this is a normalization. Now, the string coordinates, okay, are actually maps from the worldsheet to the space E, and the space has dimension small d here. And because I'm looking at closed strings, these coordinates are periodic in the x1 coordinates here, 2 pi, which is the one that describes the loop here. And back in 1970 or so, people, and in particular Nambu and Goto, wrote an action that is the starting point of the story. And it's they try to mimic what happens for point particles, which evolves on a word line. This action is proportional to the total surface area of the worldsheet, right? And there is a parameter here, which is significant, which is called the string tension. So this represents the parameter alpha prime is proportional to the square of the length of the string. And it's the parameter that appears in some perturbative expansion in order to include a stringy effect in string theory. So if alpha prime is near to zero, the tension tends to infinity. And in that limit, everything looks like the string is a point particle. And as you increase the value of alpha prime, then of course you introduce stringy effects. Now this may look a little bit obscure if you don't think for 2 minutes about this expression here. So mathematically, it's a metric in the two-dimensional space, alpha and beta label 0 and 1 here. And it's an induced metric from this space-time G mu nu metric there. And if you think of how to express the elementary surface area in 2 dimensions, well, in modulus, it's the vector product of the 2 infinitesimal tangent vectors to the coordinate lines. And if you do this in classical geometry, and then you transpose it in this language, that's exactly what you get. You get the square root of an expression, which is the square of the first tangent vector times the square of the second tangent vector minus the square of their scalar product. Okay, so significantly, this action is reparametrization invariant, which you want because it's the physics shouldn't depend on how you parameterize the worldsheet. And the other important things that people didn't really like at the beginning is that it has this square root. Why? Because when you go to the quantization of the string and use path integral methods, well, what you want is Gaussians, right? And this, if you exponentiate the action here, then you get into trouble. But fortunately, there is a cure to that. And this was provided not really by Polyakov, although this action is called the Polyakov action, but I think people like Paolo Di Vecchia were involved in actually the first formulation of it. And how does this one differ from the previous one is that you introduce new degrees of freedom here. This is the inverse of a metric on the worldsheet. H is the determinant of the metric, okay? But you see that this action does not depend on the derivative of this metric. Therefore, it's not a dynamical degree of freedom. You can eliminate it using the equation of motions. And if you do this, you land back on the Nambu-Goto string, the action, okay? So everything there is okay. You had reparametrization invariance before, you don't lose that, but you gain a new symmetry here, which is the Y symmetry. And the Y symmetry actually is one that leaves the action unchanged if we multiply the metric by a scalar factor here. So now in this formulation, we have 2 reparametrization and we have 1 scalar factor. So we have 3 degrees of freedom there, all right? It means that the metric H alpha beta, which is a symmetric tensor, has also 3 degrees of freedom. So you can fix them all. So you can actually fix the metric. And in many calculations, you put this metric to the 2-dimensional Minkowski metric. And I'm using in my conventions here, I'm using the signature minus for time and plus for space, which is a choice, of course. Right. Now, among the 2-dimensional reparametrizations, some of them change the metric by a factor here. So this is not the same as the wild symmetry that I just talked about, because here we also change the coordinates on the surface. So this is a class of reparametrization on the worldsheet, but because we also have the wild transformations and on disposal, we can undo this scalar factor here, and therefore effectively we can leave the metric unchanged. So if you had chosen the metric to be eta alpha beta to start with by fixing the gauge, then you can stay there by this kind of process. And these transformations are actually called conformal transformations, and you are familiar with on the complex plane, there's a little example of a conformal transformation, and their signature really is the fact that they preserve angles, which you can see from the grid here, which has 90 degrees between the red and the blue lines, and locally here you see that it's the same. Right, so Now I would like to introduce the energy momentum tensor, because that's for any theory that we look at. If you have a translation and invariance, then there is a conserved current associated to it, and this is the energy momentum tensor. So what does it look like here? Well, that you have to take as granted here. That's one way to access the form of the energy momentum tensor in 2 dimensions here by varying the action that I gave before with respect to the metric. And it gives you this formula here, right, whatever it is. And if you change coordinates here to make your life a little bit more easy, then the components of the energy momentum tensor, which are defined here, t plus plus and t minus minus by this, it's also a symmetric tensor there, are given by the quadratic expression in the derivative of the string coordinates. And because the string coordinates are periodic in x1, it makes sense to take a Fourier expansion, and the Fourier modes here are called L sub n and L bar sub m here. You see that the parameter alpha prime is there everywhere, and these we will see them again, these modes, very soon, actually already here. So this again is a little bit heavy in terms of formula. So the important message here is that now that you have an action, you can look at the equation of motions for the fields, the dynamical fields of the theory. So you have phi mu here. The equation that they obey is a wave equation in 2 dimensions. So you expect it to have a formulation where it depends on x naught plus x1 and x naught minus n1, called this side the left movers, this one the right movers. The coefficients classically are just numbers, but soon they will become operators. They are oscillators. And then you have something proportional to x naught, because this solves the equation. And q mu is a constant as far as the 2-dimensional worldsheet is concerned, interpreted as the position of the center of mass of the string, and p mu as the center of mass momentum. So because you introduce these, you can quantize the theory by the usual method. So you replace Poisson brackets with the commutators, usual story. You recognize here the quantization of Q and P, momentum and position. And in terms of the oscillators, we have these commutators here, which provide algebras which are very, very close to that of harmonic oscillators. And significantly here, the left operators, the left oscillators don't talk to the right ones, so they decouple. Okay, so that makes life quite nice at this stage. Now, because Ln was given in terms of the derivatives of the phi's, right? So it's not surprising that you can re-express them in terms of these oscillators. Now, that's a calculation, of course. And what you obtain are these 2 formulas here, where we have quadratic expressions in the oscillators, both for the left movers and then something I didn't write for the right movers. Now, there is a little nagging problem here when you look at the 0 modes. So suppose for a minute that I put n is equal to 0 here, and therefore, because these 2 operators, alpha minus m and alpha plus m, do not commute, yes, because of this delta m plus n there, then you have an ambiguity in how you order them. And there is a convention to normal order them by putting all the positive modes to the right here. But of course, you introduce an effect because of this choice. And this is encoded in this variable, in this constant a here, which takes into account the fact that you have normal ordered the 0 mode of L naught, right? So this again is a parameter that is going to be fixed in the bosonic string, but in general, it may move if you go to a more complicated string. Now, these modes of the energy momentum tensor obey the celebrated Virasoro algebra, and we have a central term here proportional to a constant here, which is the central charge. And it turns out that if you have D bosonic field in your theory, that central charge is equal to D. Okay. Now, this was about the equation of motions for the string coordinates. if you look at the equation of motion for the metric H, then it amounts to the stress energy tensor that we expressed quite formally before to be 0. And this introduces constraints on the theory, and we can't put all the modes acting on states to 0 that would lead to inconsistencies given this algebra, okay? But there is a slightly milder condition that you can impose that doesn't affect the physics, is that the positive modes of the Virasoro generators here acting on a physical state are set to 0. And again, the 0 mode shifted by this A parameter on the physical state is also 0. Now in the bosonic string, D is 26, turns out. Consistency of the theory requires that. That's one way to see it from this approach, but there are many other ways to justify this T was 26. And this constant A happens to be 1 in the bosonic string. And then very briefly, once you have these constraints, so L0 minus 1 on a physical state is equal to 0, actually you can extract the spectrum of these bosonic strings. So in this guise, this is L0 minus 1, because L0 had the normal ordered expression here. Now, probably you notice that I've replaced mu by I here, but that's because I've chosen to present this in a specific gauge, which is called the light cone gauge, where you put yourself in a situation where the expressions you manipulate are all going to lead to physical states. If you don't do that, if you don't go into that gauge, then you have to be a little bit more careful, because each state has to be checked against the fact that it's or not physical. So people have done that, of course, yes, but this is why this I here runs from 1 to 24, because the dimension of the space is 26, and there are 24 transverse dimensions in this gauge. And P here is actually linked to the definition of the 0 mode of the oscillator that I gave you before. Maybe you didn't pay attention, but that's where it's coming from. And if you look at this expression, there's still a minus sign in front, but this is what we call an on-shell relation, which is a relation between momentum and the mass, the rest mass of the particle, that has to be satisfied for particles that you can detect. Okay, so if you're off shell, then they're called virtual particles. They don't live long enough, right? So this is where it comes, and the fact that you have left and right matching here is also linked to the fact that the left movers and the right movers don't talk to each other. I mean, I don't need that. Just wanted to highlight the fact that if you look at the states that obey this condition here, there's the vacuum, of course, which has minimum energy, meaning no excitations by oscillators, no momentum. And then if you do this, you see that the square mass is -4 over alpha prime. Yes, by just looking at this contributes 0. And this is what we call a tachyon, because the square mass, which is negative, means that the particle traverses the light at the speed further than, higher than the speed of light, so not observed. So that's a big problem in bosonic string. On the other hand, you see the appearance of tensors here, ij, with one left mover and one right mover oscillators. And this is a signature that there is a graviton potentially in the theory, but equally, I mean, you could have an antisymmetric combination. I mean, the graviton being the symmetric combination of these two, and then you have also a scalar, which is a dilaton. Okay, and so on and so forth. But you have here a way to count states in the free bosonic string. And of course, because of all these problems, people had to consider the fermionic string to cure the tachyon problem. And because we don't want to live in 26 dimensions, we also have to go through a process of compactification that I will come back to later on. So this was all about the non-interacting string. Now here, we are going to make a brief incursion into the interacting string, especially looking at this path integral here, So we exponentiate the action I gave you before. There is a little bit of trickery here because we move to Euclidean space in 2 dimensions to improve the convergence of this integral. So there is a little bit of work behind the scenes there. The integral here is over all the embedding of the 2-dimensional surface in the space-time, and also over all the intrinsic 2-dimensional shapes of the surfaces that you have. So this is quite an interesting object to study. We are not going to do that here. We don't need to. You see that this is a sum, an infinite sum over what happens to be the topologies of Riemann surfaces in this case. Why is this? Well, I've chosen to look at amplitudes which are called vacuum. Yeah. H, the metric. This one here. Yes, yes, okay, yes, you can do that. But here you start with a general. You have to look when this object dictates that you have to look at all of them. After that, you can fix it. Yes, the prescription for this calculating this path integral is that you have to consider all the 2-dimensional metrics, all their shapes. Yes, then the fixing of the gauge, if you are classical, we did it, but here you can do it, but not at this stage. So at this stage, by definition, this object is like
You can fix it locally.
that's also true. Yes, yes, yes. Okay, okay, okay. So that's a question of locality. Okay, we can. Right. So in the instances that I'm interested in here, we look at the vacuum amplitude. So this is a bit different from what has occupied quite a bit of our workshop last week about amplitudes in the context of string theory, where we have external legs into the scattering amplitudes here. And therefore, the pictures that were drawn had little crosses put on these Riemann surfaces, which are where we insert these vertex operators in order to take these external legs into account. But here we don't. So think of this as a closed string here, which just propagates. The first term is just free. So it describes a cylinder. And then you pull these 2 strings there to infinity. I mean that you make the tension very high. And as we said, if the tension is very high, then the string appears to be a point. So actually, the topology of this becomes a sphere, while here, where you have an interaction, then you see that you create a handle in your amplitude, if you want, yes? And then you pull it to infinity here. So this is the pants, the famous pants diagram here. But by putting the tension to infinity, this becomes a torus, and so on and so forth. So the more loops you have in your handle that you have in your Riemann surface are going to describe more and more interactions between the strings. And this is also a parameter in the theory, which is called the string coupling constant, which depends on the genus of the surface that you consider. There is an offset of -2 there. And a perturbative expansion in this GS is also leading you to the quantum regime of the string. So you have the alpha prime parameter, which gives stringy effects, and you have the GS, this gives you quantum corrections. Now, what's not here are non-perturbative effects that go like e to the -1 over GS squared, and D-branes live there in particular. So, but this is not of my concern here. So what's important for us is that the string theory is formulated as a set of conformal field theories on Riemann surfaces. Now, modular transformations are important. You can parameterize Riemann surfaces by a set of parameters called complex moduli. Now, for the sphere, there is no such thing. for the torus, which is what we are going to be interested in, there is one complex modulus, and so on and so forth. Okay, and there are some reparametrization transformations that change the value of the moduli, but don't change the shape of the surface. But since the theory should be invariant under reparametrization, then the meaningful quantities that we are looking at should be invariant under these modular transformations. And it turns out that the modular invariance of the vacuum amplitude on the torus is one of the strongest constraints for a conformal field theory. You can still obtain a few informations from the two-loop partition functions, but obviously a theory that would fail modular invariance on the torus would have little chance to survive, no chance to survive. Right, so briefly here, if we look at the torus and we go to Euclidean time, introducing complex coordinates in this way, well, the torus can be represented in the complex plane by a parallelogram here with two periods, omega-1 and omega-2. So that's the setup. And along the x1, w1 direction, we have Euclidean space. And along this direction, the imaginary axis, we have the Euclidean time. So if we have our loop here of a closed string, which is period omega-1 in x1, and if you transport your string around the torus, when you rejoin, the purple point here could be at the same point, but it could also be offset by a phase. Okay, so that's an angle there, and that's encoded in what we will write on the next transparency. So briefly here, a recap of what the modular transformations are. There are elements of SL2Z, and it's a change of basis for the periods that translate into this transformation for the modulus parameter tau, which is the torus modular, which is the ratio of the two periods. Okay, so if we look at the vacuum to vacuum amplitude on the torus, this is called the Bosonic partition function, all right? And by implementing what we saw on the previous transparency, with H, the Hamiltonian of the theory, being associated with translation in time, and P being associated with this angular deficit when you come back after going over the torus, changing variable, introducing Q and Q bar here with this relation between tau bar and tau here, you can recast this expression into one that starts looking a little bit like the very formula function that I gave you on the first transparency. So it's a simplified version of what we will end up with. All right. So in order to calculate this object here, you have to trace over the space of state, the Hilbert space of state. You have two contributions, one from the oscillators. Remember, L0 as oscillators, also there's also momentum there. Now the momentum is essentially a Gaussian. So, and we are in 24 transverse dimension. So this Gaussian gives you this expression here. So the 12th power of the imaginary part of your complex modulus, okay? And the oscillators, you have contribution from left and right here. And essentially this on the left is the trace of a Q to the L0 minus 1, where we just consider the oscillators. And that can be encoded in a series expansion here in powers of Q, with integer powers, positive, and some numbers there, right? And then you just look at the spectrum of your theory. I already said a few things before about the spectrum, but basically this is an easy exercise. You take your vacuum that, okay, the Q minus 1 vacuum, usually you would see a 1, but there's a Q minus 1 because there is an offset from the energy of the vacuum, which is not necessarily 0, and it's not 0 here, it's minus 1. And then you have if you fix an oscillator, you fix I and N here, then you have a state which one oscillator, then you have a state with two oscillators and so on and so forth, okay? And therefore, if you count them, you see that the exponent here tells you the energy, so the value of L naught being the energy essentially of the state in question. So here, the energy happens to be N. Here it's 2N because you have two such, and so on and so forth. And this gives this factor here. And then you have 24 oscillators, so you can convince yourself that you take the 24th power of 1 over 1 minus q to the n. And if you do this, the oscillator contribution happens to be the inverse of the discriminant function of number theory, which is the 24th power, sorry, of the Dedekind function, which is in red here. So that's a function that came quite quickly in the story of strings many, many years ago. So the first, well, one of the first signs that number theory is important in string theory, and this comes from the modular invariance requirement. Right, so here is a definition of modular forms that I thought I should at least flick for a few minutes. The important thing is that modular forms naturally occur in string theory, and in particular, when we want to build modular invariant partition functions. Yes? Yes, yes, okay. So I try to explain that you want to make sure that when you have a torus, it has a parameter called tau. Now, if you reparameterize in a certain way, the modulus can change, but the shape of the surface shouldn't change. Okay, so you want to ensure that whatever theory you have has this symmetry. That's coming from there. That there are reparameterizations. They're global. You see, they're not local. These ones. Yeah. Okay. So to summarize, the torus partition function is given by this expression, and the Dedekind theta function here to the power minus 24 is not quite modular invariant. Okay, there is a factor there that you have, but it's actually compensated by what comes from this imaginary tau factor. So if you change tau to A tau plus B over C tau plus D there, you get something, and then you would see that all in all, momentum and oscillators just combine and give you something modular invariant. So it's quite satisfying. Now, you can write conformal field theories, bosonic, which are not the one I just described. This was motivated by string theory. And in this case, the bosonic, the partition function of the theory is again written in terms of a trace like before. And here, instead of 1, I have C over 24. Remember that for the bosonic string, C was 24 or 26, but sorry. Yes, there is to be a bit careful here. So this factor here has to go to -1 in the bosonic string. And the trace in the left and the right sector here are given by the characters of the Virasoro algebra. Okay, so there is a whole industry here that started in the 80s to calculate representations of the Virasoro algebra, okay, which are called highest weight irreducible. So you start with a weight A, and you hit it with the negative modes of L, because the positive modes would give you 0. And you see what you get. And sometimes you get states that have 0 norm or negative norm. So they are not physical. So you have to extract them from your counting. And if you do this in a systematic way, you obtain the characters of the Virasoro algebra. Of course, this is a generic case where nothing terrible happens down the line when you hit with the modes of L. Okay, I haven't written the other ones because it depends very much on the central charge that you take, and it depends on the value of this energy, so the eigenvalue of L naught on A. Okay, so it's a beautiful piece of mathematics that was carried on by Rocca Caridi in '84, And since then, of course, people have used and abused this representation theory in statistical physics. Okay, so critical phenomena in statistical physics, calculation of the exponents, and there is a new life for all these things now with the bootstrap program and so on. So it's very right. So if we want to count, if you want to look at a slightly more sophisticated string theory to cure the tachyon problem in particular, then we have to introduce fermions. And physically, we want this because in real life, we see particles which are bosonic and fermionic. So we do this. So in this particular setup, we introduce as many fermionic degrees of freedom as bosonic ones. Okay. And we impose a very special symmetry between bosons and fermions with the help of spinors here, which are anti-commuting. Okay. Depending on the code, on the x, on the x naught and x1, and this is called a local worldsheet supersymmetry. So once you introduce supersymmetry in physics, the equations are becoming quite complicated, right? So don't expect you to really, analyze this action here, but simply to notice that alongside the partners of the bosons that are psi's, we have to also partner the metric H alpha beta with this object here, chi alpha, which is called a gravitino. Okay, so that's in passing, but this is the action that you have to work with. The rows here are actually satisfying a Clifford algebra. They are gamma matrices in 2 dimensions. Okay, so they have hidden indices here that you don't see, which are spinor indices. They talk to the psi here, and then of course, I mean, it's more complicated to handle, but at the end of the day, we have conformal invariance. We keep conformal invariance, and we have this new supersymmetry, and therefore you expect your algebra of currents to be enhanced. There's more in it than just the Virasoro. And indeed, that's what happens. These 2 currents are the energy momentum tensor, that's the conformal invariance linked to the conformal invariance. And we have another current, which is called a supercurrent, which is associated to the supersymmetry. So you go through the same ideas for the bosonic string. So you introduce oscillators. But now, because fermions always appear in bilinear combinations in all physical quantities, okay, then you can choose periodic or anti-periodic boundary conditions for the fermions, something that for the bosons we had to take as periodic. Okay, so here in the x1 direction, which is represented by these plus and minus signs there, then the fermion could be anti-periodic or periodic, and in physics, they have names. When it's anti-periodic, it's called a Neveu-Schwarz, and if it's periodic, it's Ramon, all right? But this is in the x1 direction, but nothing stops you from also putting anti-symmetric boundary conditions in the other direction, in the direction of x naught, okay? And the way to implement this is to introduce in the partition function this -1 to the fermion operator. So this is an operator that anti-commute with D's and B's, these oscillators for the fermionic string, and they count the number of, so it spits out a +1 if you have an even number of fermions, and a -1 if you have an odd number of fermion in your state that you are constructing. And these are called the Neveu-Schwarz twisted. It's twisted by this operator, because what happens essentially is that you evolve your string and then you flip the sign before re-gluing the second part of your cylinder to make a torus. And again, nice functions happen when you do this, when you can the states here. And these are the Jacobi theta functions that come in. And the 4 in principle come in. So θ3, θ2, θ4 in this version of the model where we are just having functions depending on tau, on the modulus. This one happens to be 0. But in generalizations, you will see that θ1 appears because it acquires a second dependence in a second variable. Okay, so for this fermionic string, the consistency requires D to be 10, so not 26 anymore. And this constant that we had to shift the L naught by are either 0 or 1/2. Right? So just that's what happens. And now in this very version of the fermionic string, you have to do a little bit of a trick in order to get a modular invariant partition function, which is called the Gso projection. Okay, so you have to introduce minus signs between. Okay, so first of all, why is the power 4 here for the blue expression here? Well, this is the fermionic partition function of the previous page, which had a square root in it, square root of a θ3 over eta. Okay, but you have in the light cone gauge in a theory in 10 dimensions, you have 8 transverse degrees of freedom. So that's why you have a factor 4 here, which is 8. And then you have the square root, so 8 divided by 2. So that explains the contribution from the fermions. The contributions in red is coming from the bosons, because it's a theory with as many bosons as fermions. So this is what we saw in the bosonic string. It's still there. What is, let's say, specific of this theory is that you have to introduce a minus sign between different contributions depending on the spin structure, which is linked to the picture of the previous space, in order to have something invariant. And also, the two first term here can be encoded in this trace, okay? And it's just right to get rid of the tachyon. Right? This is because the tachyon is a state with no oscillators, and actually this trace gets rid of all the states with an even number of oscillators. Okay, so that's why we call it a projection. And GSO are Gayotzi, Shirk, and Olive. Okay, so famous. Okay, so the algebra underlying this theory is a superconformal algebra, because now we have the generators of supersymmetry that enter the game. Okay, and again, you can look at the representation theory of these objects, calculate the characters. Kiritsis is one of those who produce these. And now we are ready to come to what I want to say about this formula at the beginning, right? Okay, so we have come from 26 to 10. It's not satisfactory yet. We want to be in 4 dimensions eventually. So we need to come with ideas to reduce the number of visible dimensions. And therefore, we try to compactify on a space which has 6 internal dimensions that are so small that you can't just detect them. Now, that's roughly the idea. And if you do this, you start having an infinite number of possible solutions in 4 dimensions, it turns out, and nobody knows which one is privileged. Okay, so there's no dynamic that guides us towards what would be the solution that is acceptable. Okay, I should mention that the previous string that I presented is really looked at from the point of view of the worldsheet, because the phenomenon I'm going to describe comes from there. But of course, we have Mike Green in the room here, who created a revolution in 1984 with John Schwartz, by reformulating the superstring theory in a way which is manifestly Lorentz invariant, and which is anomaly free. So because anomalies are little problems in the discussion of the string in general, and that's usually the way that people now look at the superstring. Okay, not the one I presented, but I did it for the purpose of this talk. Okay. So this is a little cartoon of what compactification could be. And in particular, we have, we could compactify on a torus, which is a flat manifold, but the formula that I showed before has to do with compactification on a very specific Calabi-Yau manifold, which has two complex dimensions. Now, the story about Calabi-Yau compactification initiated in physics with the work of Philip Candelas and collaborators there, Horowitz, Sturminger, and Witten in 1985, yes. Beautiful, beautiful theory, a lot of insights, the constraint that you have to put on manifolds in order to hope to see something that you could detect in an accelerator. Nothing has been discovered so far, but I mean, it's really nice. Now here, I will specifically look at the K3 manifold, which is a hyperkähler manifold. It has not just one species of supersymmetry on the world sheet, it has 4. And this is linked to the fact that this is a hyperkähler manifold, so there are more than one complex structure, and therefore altogether it amounts to 4 world sheet supersymmetry in space-time, because obviously space-time always talks to world sheet. These manifolds allow you to have 2 n equals 2 space-time supersymmetry. But again, I'm interested in the world sheet ones. Okay. Of course, this is just a step towards 4 dimensions. I'm not pretending at all to do something physical here, necessarily. I'm stopping in 6 dimensions, but that's not the point of this talk, to try to reconcile this with nature. Okay. So the action in this case, okay, you recognize roughly what I wrote before. Now the metric of this internal space here could depend on phi. Okay, so that becomes more and more involved. And because of that dependence in phi, we call this a non-linear sigma model, right? So big complication in the problem, but also much more structure. And we have the curvature tensor Rijkl of the internal manifold that enters the game as well. And this curvature, okay, plays a role here in what I have to say. Now, first of all, I've put one definition of a K3 surface there, right? It's a simply connected compact complex manifold of complex dimension 2 with a nowhere vanishing holomorphic form. Okay, and I'm going to use this in a minute. Now, such manifold as SU2 holonomy. So holonomy, the group of holonomy is the one that encodes how the parallel transport of tangent vectors are affected our tangent vectors are affected by parallel transport on the manifold. And it's SU2 for K3. And what it does in this context, I think I've lost the battery must be down. Right. So it actually breaks a symmetry there. Which symmetry is it? Well, if we were on a flat manifold, the fermions would generate a current algebra, which is called SO4. Yes, thank you. That's a good idea. Thank you. And SO4 here, right? And SO4 is locally isomorphic to SU2 cross SU2. Okay. And the effect of the holonomy actually break this current algebra to SU2. This SU2 contains a U1 in particular. And this U1 current, okay, is actually given here by a bilinear in the fermions, okay, which have an index running on the manifold. And here I have a complex notation. So I and J bar means complex variables. The complex manifold, I can do that. And this is the metric of the K3. And the unique holomorphic 2 form allows us to construct another bilinear here between the fermions, okay, which I call J plus, and another one with the anti-holomorphic version of it, okay, which are called J minus. And it turns out that these three currents here generate the SU2, the SU2 that is left over there. And when you mix this with the conformal symmetry and with the n equals 4 world-sheet supersymmetry, you get all these currents, and they form what we call the n equals 4 superconformal algebra in 2 dimensions. Okay. And again, you can look for the characters, the representations and the characters of this algebra. And now you see that we have a refinement in the character, because we have 2 operators, L0 and J0 here, which are in the Cartan subalgebra of this algebra, okay? And we can look at their eigenvalues, and you can label these representations by the eigenvalues of L0 and J0, sorry, which are H and L here, okay? So this is a label for these objects. And I've introduced a new variable y here, e to the 2 pi I mu, where mu is a complex variable. So you see that this object now depends on tau and mu. These are the 2 complex variables that I was referring to before. Now, again, this is just to give you a flavor that when you see these n equals 4 characters written in the modern parlance, then I'm not written like this, but here I thought I would write them like this so that you get a feel of where things come from. So first, let's start with this one here. So this is one type of representations where there is nothing really fancy happening when you hit the highest weight state with your generators. So you don't get 0 norm states in the middle of your Verma modules, as it's called. Okay, it's called a generic type of representations. And you see that you have these factors that look very much like the fermionic factors that we had for the fermionic string. Now, we have 4 fermions, we have 4 superconformal generators, G in this story, yes, for 4G currents. So you see that we have 1, 2 here, and then it's power 2. So we have 4 of them. So that makes sense to have this kind of power here. So this count states that are obtained by hitting the highest weight state with these superconformal generators. This one here, you can view, sorry, as the conformal generator L, okay? And in these guys here, you have the bosonic contribution as well. Okay, so this factor in front here, it's because I've written this character in the Ramond sector. Remember the spin structures, and in the Ramond structures you have the ground states of 0 modes, which is not just one state. Okay, and in this theory there are 2 of them. So that's linked to this. Sorry, there are 4 of them in this theory. Okay, so that's the way that they were constructed. Now the other ones are more involved. This in purple here is linked to the action, the free action of the SU2 generator, but there are 0 norm states coming in this type of representation. And this bracket here actually identifies where these null states, these 0 norm states are. And this is a construction that was initiated by Katz in the case of SU2, Katz-Moody algebras, and we have adapted it to this case here. So this was done a long time ago. Nowadays, these characters are written, no, this actually was still written in the 1980s, okay? And we had noticed that in the expression of these characters, you have a very interesting function here, which is very, very closely related to the upper Lurch sum that Zweigers used elegantly in his thesis many years after this particular instance there. So we knew how these H3 transformed under the modular group. That was in the literature. It's called the Mordell integral, but it's the beginning of a new bridge between particle physics and number theory. Okay, so that was the beginning of it. And then, of course, the upper Lurch sums. You can rewrite things like this in terms of upper Lurch sums that depend on mu and tau. The ones in Zweigers have even a third argument. But what comes here is a little bit more specific. Okay, so if we count now in these theories that we are looking at, the partition function in the Ramond sector, so that's not the only one you have to take into account, but that's the sector that will lead us to this function of the beginning, okay? So we trace over the left and the right sector of the theory here, and we keep the dependence not only on the energy of the state, but also on let's say, I'll say the isospin content because you have an SU2 there. So it's kind of the SU2 isospin. And that's counted by this variable y there. So you've got quite a lot of information about all these states, energy level by energy level. Okay. And you can describe these partition functions in terms of the characters that I wrote before, the ones, the first two that were quite specific and which had null states in them, zero norm vectors, and those that don't, the generic ones, called non-BPS. So you have a quadratic expression involving these two species of representations in different combinations. Now, it turns out, and that's a problem that has not been solved, is that we can't write a generic partition function with modular invariance there. We can only look at very specific models, okay, from which we learn a lot, but okay, we would like to learn more. And these are the orbifolds, torus orbifolds, and the so-called Gepner models that I don't have time to go into. But it's because we knew that we could write partition functions in these theories that we made progress. And I'll tell you why that's significant. So we wrote a partition function in these specific models, and then guided by what Witten had done in the context of n equals 2 super conformal algebras that I've not discussed at all here, okay, we have considered a specialization of this partition function where you introduce, what you do is that you shift, you introduce this operator -1 to the J03 minus J bar 03, which amounts by shifting e to the 2i, y was e to the 2 pi I mu. If I shift mu by a half, okay, mu plus a half, that produces a minus sign in your partition function, and this is encoded in this expression. So you do this left and right, and then after you've done that, you set y bar to 1. So you don't see any y bar here, but you have acquired this factor here, which is a -1 to some Fermion operator, really. So it acts, it actually acts like a fermionic operator, a Fermion number operator. Okay, now this object is called the elliptic genus of the conformal field theory because that's where it's coming from. But the beauty of this is that it's equal to the elliptic genus of K3 surfaces, which is a completely geometric object calculated by mathematicians in the 80s as well, okay? And Witten is the one who noticed that you had this correspondence between the two. So this is one way to access this information of geometry, okay? And this is where what I'm going to say in the next transparency is lying, is actually in this sector here. So by setting y bar to 1, you actually make this sector, the sector non-BPS on the right-hand side here disappear, okay? And if you look at the states that come from these two subsectors here, you see something really nice. Now, this object being equal to this elliptic genus is an invariant, but it's an invariant over the space of all the K3 theories. So not just Gepner models, not just the orbifold, torus orbifolds, but any other theory that you might think of that nobody has constructed so far, okay, in that moduli space. So it means that you can pick a particular model in order to extract as much information as you can from this. And what happens is that when you put the characters in this bilinear with the -1 to the J03 minus J03, and you reorganize the contribution in terms of characters, as you expect, okay? Okay, you have this sector here, which is not of a concern at the moment, but we have this. So we have 90 of a generic n equals 4 character at L0 eigenvalue h equals 1 and isospin 0. And you see that the isospin 0 in this expression is always there. So it's always isospin 0 representations. But what changes here is the energy. So this is proportional to Q, energy 1, energy 2, Q square, Q cube, and so on. So inside there is a Q expansion of a function, and I'll show you what that function is in a minute. But okay, so these numbers were known to us in the 80s, okay? So Oguri is the one who really published them, okay, in his thesis, and Katrin Wendland also independently reproduced these numbers in her thesis. She wasn't aware of this work, okay? And we couldn't do anything with these numbers. We were a bit stuck, right? And in 2010, there's the shaking I was talking about, okay? Toru Eguchi, who knew a little bit about Mukai's work, by the fact that all the symplectic automorphism of K3 surfaces are subgroups of M23, so a sporadic group that was already very big, had the idea of opening the atlas of finite groups. And he looked at M23, and it wasn't fitting quite. And then he flicked to M24, and miracle, okay, all these numbers here in blue are twice the representations, the dimensions of the representations here. These ones are irreducible representation of M24, but of course this is an infinite sum, okay? So you only have 26 irreducible one, but the miracle continues. You can decompose all the higher coefficients into a sum of irreducible representation of M24. And this was proven by Terry Gannon mathematically a little bit later, okay? So, okay, the story doesn't stop there because this has to do with a trace taken on the identity element. That's the class 1A, but you have other conjugacy classes, 26 of them in M24, and you can take traces with these elements or representative of these classes inserted. That was inspired by work on monstrous moonshine. And again, you find that the numbers come out as numbers in this table, okay? So this was work done by Gabadil, Miranda, Chang was involved in this, and Eguchi and Ikami. So everything points to M24 having something to do with these string theories, okay? And it has to do with number theory as well, because this function I was alluding to earlier, powers of Q here, okay, is an example of a mock modular form, okay? And again, Zweigers has developed the theory of mock modular forms in his thesis, but Don Zaghi, of course, is also very much involved in this type of work, okay? So at the level of the physics, it's good to know that you can put a name to this function, but what we don't know is, and we don't know today, is why this has to do with the string theory. What is this huge finite symmetry has to do with string theory? We are kind of used to small discrete groups in physics, Z2, Z3, this kind of things. M24 is gigantic, okay? So that's the puzzle. And to end, I would like to highlight that with Katrin here, since 2010, of course, we have really been intrigued by this. And we stayed at the level of this Mathieu 24 Moonshine, okay, trying to come with a creative idea, which is called the Symmetry Surfing Program, which we don't know if it's going to survive further tests. But at the moment, I mean, nobody has managed to kill it yet. So we are continuing to work on this. We have managed to argue for the existence of a group, which is called the octard group. Okay, it's Z2 to the 4 product, the alternate group A8, right? Which is a subgroup of M24, which is not in M23. Okay, and therefore there is a chance that we've kind of gone over one of the difficulty in the problem, but we don't know, of course. And we can generate this symmetry. We know the generators, and we also know that we are just missing one generator in order to get to M24. But of course, the difficulty, we could even write a generator that generates the whole of M24 from what we know. But the interpretation of this generator, I mean, it's one among many, we don't have. So that's really where we are. And we are obviously not the only people working on this, although I only highlight a few here because, well, there is a body of works on this. Some of the people who are involved are in the room, of course. And just to end, let me just read this, is that the techniques of monstrous moonshine can be borrowed up to a point, but we need more. And people have done so, and Roberto is here has done beautiful work in that respect. Then M24, so Mathieu 24 is the tip of the iceberg, and Jeff Harvey, who is also here with Miranda, who is part of this workshop as well, and John Duncan have done many more. They started working in 2013, but there's much more about that in the literature. Roberto was also involved in this also quite influential paper where the Mathieu symmetry is not the symmetry of any conformal field theory on K3 that we know. It's not possible. Okay, so that's saying that this symmetry is of a different, if it exists, if it's there really, as we think it is, it has a different nature. It's not a symmetry of the full partition function of the theory, right? And that's what's new. It's the symmetry of a subset of states there, okay, that is very, very particular, okay? So that's right. And the fact, yes, that's it. Okay, so I already mentioned Terry here, Gannon, because he showed that mathematically it was really M24 we are talking about. And then this group of people here, Gabardine, Keller and Paul, and Keller and Zade, they have done quite, let's say, involved calculations, sometimes in perturbation of conformal field theory, sometimes not, depending, that indicate that the symmetry surfing program has a chance to live, all right? So it doesn't contradict it, it's encouraging, and this is the reason why I talk about it today. So thank you very much for listening.